Hello, everyone, and welcome to another episode of Kelly Telly. I'm not sure if I sound robotic again, but if so, fortunately, you just have to bear with me. Today we're going to be talking about heat and temperature, following on from our discussion yesterday on the particle theory. Now, the heat and temperature, I got a couple of slides to go through, and then I've got actually a simulation that should hopefully help clarify a few things. So let's get started. Okay, first thing we're going to start off with is heat. So what is heat? First thing, and one thing that I really want you to keep in mind, is that heat is a type of energy. So it is the first type of energy that we've looked at this term, and you need to understand that it is a type of energy. So it's something that we try and measure. So what actually is it? So heat is a measure of the total kinetic energy of all particles of a substance. So going to the examples we were talking about yesterday, so say we had some sodium chloride, each of those atoms has a certain kinetic energy, and if you added up all of the kinetic energy of every particle in a substance, that would be what your heat is. Okay, now do we need to know how to measure heat? No, that is basically year 11 and 12 level content. All we need to know is that it's a type of energy and it's a measure of the total energy. Okay, what are some things that give off heat? I mean, obviously, we have fire, we have flames, we have the sun, things like that give off heat energy. All right, let's look at temperature now. So, temperature is a measure of the average kinetic energy of the particles of a substance. Now, this is where it kind of gets a little bit tricky, and I need to make sure that you understand the difference between heat and temperature. So, whereas heat is the measure of the total kinetic energy of all the particles, temperature is a measure of the average kinetic energy of the particles in any substance. I'll explain what that means in an example on the next slide, but just keep that in mind. It's measuring the average kinetic energy of the particles. So temperature is measured using a thermometer, as you know, and we do need to know how to read a thermometer and measure temperature that way. So we've got a little diagram I pulled out of your textbook here. Basically, it talks about the three different scales that exist for temperature. So temperature is measured in degrees, but there's different scales that we can actually read those on. The one you would most commonly know is the degrees Celsius scale, and that is the one that Australians use to measure temperature. Most countries throughout the world do. Um, Americans, on the other hand, use Fahrenheit, the Fahrenheit scale. And finally, we have Kelvin. This is a scale you might not have come across yet, although I think we did touch on it in term one. Basically, it is a scale that scientists use, and this is goes back to the point I was making about scientists using a universal scale so that other scientists can understand their work. So all reputable scientists, they convert all of their temperature measurements into Kelvin, so that other people around the world, no matter whether they're from America or Australia, they have a universal scale here to use. So yeah, basically this is a thermometer. The way a thermometer works is actually to do with the particle theory. So we have a substance in here. It used to be mercury. Now it is, I believe it's ethanol, some form of ethanol. Basically, you put this into a solution. This temperature measures the heat. It measures the temperature, not the heat. Measures the temperature because these the particles in here expand if they're being heated. So from a liquid into still a liquid, but one that is the particles are more spread out. This is probably the trickiest part, but hopefully this example on the next page will help you here. So here we have two saucepans, and again I pulled this from the textbook, and there is an explanation in your textbook about what is the difference between these two. But I'm just going to give it a go explaining it here, and then you also have the textbook to help you out. So in both of these saucepans, they both are at 100 degrees Celsius. Okay, so they're both measured at 100 degrees Celsius. This means that the average particle kinetic energy in both of these is the same. Okay, so on average, so say this had maybe 50 water molecules. We know it doesn't, but let's just pretend it does. And this one, let's just say it has 100. Okay, both of these have an average has the same kinetic energy. So each of these particles, so say there's 50 of them, right? Let's just say that the total energy is 50. Okay, meaning that each of them, actually, you know what, we can use the example that actually gives us. So if we have a think about, it's 100 degrees Celsius. So let's just say the average speed is 100 degrees Celsius. Okay, the average kinetic energy is 100 degrees Celsius. Now, if there were 50 particles, it means that each particle would be going in whatever units that's in. Okay, you don't need to worry about this. I'm getting a little bit advanced. I'm just trying to help, and now I'm starting to think that it's getting a little bit too confusing. All of these particles are going twice the speed, but on average, it means that they're going 100 degrees Celsius. Okay. In this 100 one, they're all probably going 1 in whatever unit that's in, which also adds up to 100 degrees Celsius. Okay. So this is the average here. Okay. And these ones are the absolute values. So what does that mean? Okay, you know what? We've lost it a little bit here. Let's just go back to the start. Each of these saucepans contains water that is currently at 100 degrees Celsius. So that means that every particle in here, and in here, has an average kinetic energy of 100 degrees Celsius. Now, which one, however, has more heat? Now, this answer is a little bit more tricky, but it actually has to do with the amount of water. So if you'll see, saucepan A has less water, and saucepan B has more water. Therefore, saucepan B has, let's just say, double the amount of water. Therefore, it actually has double the amount of heat overall, more energy overall, okay? So that is how I want you to think about the difference between temperature and heat. So temperature is the average. Temperature is the average equals the average kinetic energy. And heat is the total. And heat is the total. Okay, so hopefully you understand that. I lost it a little bit there. In that example that I was writing up here, I'll explain that further in class or when we have our Zoom sometime this or next week. Okay, so just pay attention to that. But I am just going to show you a quick simulation that will hopefully help you with that. So here is a simulation that is basically the states of matter. Now, I'm going to post a link to this so you can have a little bit of a play with it. But basically, it gives us different atoms and molecules up here and the different states that they're in. So if I go to water, right, the example that we were just using, and we can look at the solids, water in solid form. We can look at the water in liquid form, and we can look at the water in gaseous form. We can actually play with this little device down here, and this increases the amount of heat or decreases the amount of heat, which we say is cooling. Okay, so basically there is a little toggle here that you can either increase the heat or decrease the heat. So if we go to a solid, remember the particle theory. Now this is where the particle theory links with the heat and temperature. If we add more heat, we see here that the solid, right, is going a little bit. It's going to let's start again. It's in the solid form, and we heat it up, and it's actually going still at negative 16 degrees, so it would still be a solid because water starts to become liquid at 0 degrees Celsius. it goes between freezing and melting at 0 degrees Celsius. So now we can increase the heat a little bit more. You should see it slowly kind of become more like a liquid. Right, so it's 70 degrees Celsius now. It should probably be close to a liquid. You can see it moving over each other, but a little bit more freely, a little bit more random than the solid. And finally, when we hit 100 degrees Celsius, that is when it starts to become a gas. Okay, so this is where the more heat you add, or the more you cool it, which again is just taking away heat, you can see that it changes shape. So I'll be sure to post this when I'll link it with your work that you guys receive. So have a bit of a play with this. Hopefully it'll help you to understand it a little bit more. If you got a little bit confused between temperature and heat, just remember that heat is the total energy. So if there are 100 particles of oxygen here, that is going to have more heat than if you have another container that has 50 particles of oxygen. Okay, so it's just the amount of particles also contribute to the heat. Okay, the temperature is the average. So if you have one and it's going at 100 degrees Celsius, then your total is 100 degrees Celsius. But if you have four going at, if you have maybe two going at 100, then it's going to have more temperature than the same amount of particles. Okay. I'm going to say that one more time just to make sure that you understand. Okay, so let's just go here. We got solid oxygen. Okay, its heat is based on the total amount of kinetic energy that these particles have. See, they're all moving. The temperature is the average kinetic energy of those particles. Okay, that'll probably do it for this episode. But if you have any questions, please comment them on the video or ask them to me on Edmodo or a private message if you prefer. Okay.